Exercise 1009 is the last exercise in this chapter, and it's on further exponential growth and decay. So last lesson we looked at growth and decay, where the rate of change was proportional to, or some multiple of, the amount in the population, or the quantity that we're looking at. And we saw that n equals ae to the kt was a solution to this equation. But often in real life, this is not actually a correct model. So there is a modified one that we're going to be looking at today. So this model that's often a little bit more realistic in certain situations is where the quantity, so the rate of change is proportional to, or a multiple of, the difference between the quantity and some fixed amount. A perfect example of this is Newton's law of cooling, and I would use that as an example. So this modified scenario, this equation here is a solution to this, and I'm going to prove that. So where the number of whatever it is in the population is equal to P, which is a fixed amount, plus A times e to the kt. So it's like e to the kt, but shifted up by P. So we'll also look at the graph of that. So I'm just going to prove that this is a solution to this equation. So if n equals P plus ae to the kt, the first thing I'm going to do is I'm actually just going to subtract P off each side there, because I just want to know what n minus P is equal to. So n minus P is equal to ae to the kt. That's going to be useful in this proof. Okay, so let's differentiate this. So P, remember, is a constant. So P is just going to differentiate to 0, because it's just a number. And there's ae to the kt, so we need to use the chain rule, so the k comes down the front, and ae to the kt differentiates, well, e to the t differentiates to e to the t, so e to the kt. So chain rule, we've multiplied by the derivative of the inside of the function. Now, this a to the kt, we've just seen right here that a to the kt is equal to n minus p. So we can see there that that is a solution to this scenario. Let's just quickly look too at what happens at the initial values. So when t is equal to 0, time at the beginning, back into the original equation, we get n equals p plus ae to the k times 0. Of course, k times 0 is 0, and e to the 0 is 1. So that's p plus a. So in this scenario, the quantity at the start is p plus a. So in our previous exercise, a was the quantity at the start. It's now p plus a. I'd also like to look at the graphs of this situation. So when k is positive, that's when we've got growth, remember. When k is negative is when we have decay. So in this situation, as our k is a positive number, we are going to have a positive exponential value, but it's shifted up by p. So instead of the x-axis being the very bottom of the graph, we would actually have this p value as being the bottom. Now, if you can imagine what it would be like if time was negative, we would start like that. But we don't do t negative, so we don't do this part of the graph. So somewhere up here, we're going to have a growth like that. So that's the result when k is positive. If k is negative, then it's like we've got a negative in front of our variable, so it's kind of like a reflection through the y-axis. Again, our p value in this case will be an asymptote. It's still like it's shifted up, but instead of going up, we're going down. Something is, so this is a prime example of what I was talking about, Newton's law of cooling. It looks like that. So p is our asymptote. So in Newton's law of cooling, what happens is you've got something that starts as a temperature up here, and this is the temperature of the surroundings, like the room temperature. If you're thinking of a hot cup of coffee, for example, It starts out at this temperature, the temperature comes closer and closer to room temperature, but it's not exactly going to fall below room temperature. It's always going to stay close. It's going to eventually even out to be very close to room temperature. The mathematical model shows that it never actually reaches to room temperature, but obviously in real life, room temperature changes. So if that room temperature were to rise, then technically speaking, that cup of coffee would warm up with the room temperature again as well. So this model doesn't really apply over time once that P changes. In this model, P is a fixed value, so it's like room temperature doesn't change. It's stuck at, say, 23 degrees all the time. I'm going to do two examples, one on growth and one on decay. So in this example, a population's growth rate is proportional to n minus 3,000, where n is the number of people and time is measured in years. Show that n equals 3,000 plus AE to the KT is a solution to this equation. So I'll just write down that equation again. N equals 3,000 plus AE to the KT. Now the first thing I do want to do here is just minus 3,000 off each side, like I did in that previous part of this exercise. So I get n minus 3,000 is equal to AE to the KT. And that is really helpful if you remember to do that. So let's look at the derivative. So dn dt, just looking at this line here, 3,000 becomes 0. AE to the KT, we times by the K, so it's KAE to the KT. And of course, AE to the KT, we've seen right here, is n minus 3,000. So sure enough, it is a solution to this particular situation. In part B, we're asked to find the values of A and K if the population is initially 4,000 and grows to 6,000 in 5 years. So let's write down our equation again. And we're going to plug in those values to find them. Now it's always easiest if you plug in the initial values first. So we know that when t equals 0, initially, that n is equal to 4,000. Which means A is actually going to be 1,000 because P plus A is always the initial, but we do need to show that. So 4,000 equals 3,000 plus AE to the K times 0. So that whole thing is just A times 1. So A equals 1,000. It's fine to sort of skip that step a little bit. So N equals 3,000 plus 1,000 E to the KT is where we're at the moment. Now we do need to find our K, and to do that we plug in those second values that we're told, the 6,000 in 5 years. So that means we're at 6,000 equals 3,000 plus 1,000 E to the K times 5, and we just solved that equation to find K. So let's take 3,000 off each side. So 3,000 equals 1,000 E to the, instead of K times 5, I'm just going to write 5K, divide by 1,000. So I'm just going to switch it around, put the E to the 5K on the left, and this side is now just 3. Now let's take the log of each side, natural log, because our base is E. So this side is just 5K because the log and E cancel each other out. And then let's just divide by the 5 to finish up. So K is equal to, I'm going to write that as 1/5 log 3. We'll write down what that is as a decimal. I don't tend to like to use it as a decimal myself. If you do put a decimal in, remember, put lots and lots and lots of decimal places so that you don't mess up your equations. Just a useful trick with the calculator that I tend to do. You can see I've got 1/5 log 3 in there. I don't actually need to close the bracket on the end if it's at the very, very end like that. I put it in my calculator. I like to store that in my calculator's memory. And this RCL button helps us with that. If you look just above it in yellow, it says STO for store, because in yellow we press shift first, so shift store. And then I just press any of these buttons here with a letter on it. I'm just going to choose that one. So I've now stored that number in my calculator under the letter A. So in order, I'm just going to clear my screen. In order to get that back, I just go alpha A. Notice I didn't press alpha when I stored it, but I do press alpha now when I bring it back, and I press equals, and there's that number again. So part C asks us, what's the population after 20 years? I've just written our model as it is now. So I've now, instead of A, I've got 1,000, instead of K, I've got that number there. I could have written that in the page as a decimal. That's not a problem. That's the way your textbook does it. I'm a big fan of exact values, so I've left it like that. So after 20 years, that's when t equals 20. So 3,000 plus 1,000 e, I'm just going to put k there, times 20. Now I'm going to use that number that I stored in the memory of my calculator to calculate this. So I'm going to put in the 3,000 plus 1,000, shift log to get e. So for k, I'm just going to go alpha a, and that's that exact value, so there's no rounding going on there. Well, no more rounding than what the calculator's done itself at 8 or 9 decimal places, times 20, and there's our value, and that's a nice round number too, which is really handy. So 8400 is the population. I'm going to put people because it mentioned they were people, and it's always nice to have units. In part D, after how many years will the population reach 200,000? So what we want to know is what's the t when n equals 200,000. So 200,000 equals 3,000 plus 1,000 e. I'm just writing that k again. I know what my k is, I've got it down. It is good to put some numbers there in an exam though. It's just a little bit of a shortcut that I'm using. So I need to minus off the 3,000. Technically, if I wanted to, I could have actually started by dividing everything by 1,000, as long as I divided everything by 1,000. But this is the way we normally do it. So 197,000 equals 1,000 e to the kt. Let's divide by that 1,000. So I've got 197 equals e to the kt. Let's take the logarithm of that to get rid of that e. So, and I'm going to turn it around as well. So kt equals log 197. So t equals log 197 divided by our k. Just show that working out there as well. And again, to put that in my calculator, I'm going to use that a value again. So I'm going to put in log 197. I do, of course, need to close my brackets there, and I'm going to divide that by alpha a, because remember, a is my k value. And there's the answer, just over 24 years. So 24.044896, blah, blah, blah. Now, depending on the wording of the question, it's interesting how you might write your answer here. It is over 24 years, but it's only just over 24 years. If they were saying how many whole years will the population first be over 200,000, you may need to give a word answer where you've said it's over 24 years, so after 25 years is when they were over 200,000. But in this particular case, I've just put they were over 200,000 a little after 24 years. Example 2 is almost exactly the same, except for the fact here our k is going to be negative because we're looking at decay rather than growth. So in this example, we're first told that Newton's law of cooling states that the rate of change of cooling is proportional to the difference between the temperature of the object and the room temperature. So what that means is if the room temperature was 23 degrees, the rate of change of the temperature, so capital T is temperature, lowercase t is time, is equal to some multiple of, or proportional to, the current temperature of the object minus 23. I've just added there that capital T temperature, lowercase t time. So in part A, we're asked to show that t equals 23 plus ae to the kt is a solution to this model. So this is exactly the same as what we did last time. The first thing I want to do is minus 23 from each side of that. So I want to know what t minus 23 is equal to, and that's ae to the kt. Now I want to differentiate my equation. So dt equals 23 becomes 0, ae to the kt becomes kae to the kt, which equals k times, remember ae to the kt is t minus 23. So instead of ae to the kt, we've got t minus 23. So therefore, yes, it is a solution to that model. So part B here really throws us in the deep end, because it's not scaffolding this question at all. It's not telling us anything really at all. We know the room temperature. We know that the water was originally boiled to 100 degrees Celsius, and after 10 minutes it dropped to 65 degrees Celsius. But that's all they're telling us. We want to know how long will it take to reach 25 degrees Celsius. You do need to follow the same process. You need to write your equation down. You need to find your A value, you need to find your K value, and then you can use that to solve the problem. So let's do that. So we were already given in part A what the equation is. So we know that t equals 23 plus ae to the kt is a solution in this situation. I still use that 23 degrees for the room temperature. So we always start with t equals 0, that the temperature will be 100 in this case. So at the start it was 100 degrees. So 100 equals 23 plus ae to the 0. I've kind of skipped a step from what I did before. But then we can minus the 23, and we can see that a is equal to 77. So our equation is now t equals 23 plus 77e to the kt. Now we use those second numbers that they've given us to find the k. So they've told us after 10 minutes. Now, t can be in whatever units we want. So if you wanted to set it to minutes, set it to minutes. If you want to set it to hours, set it to hours. Just be consistent throughout the whole problem. So it seems obvious to set it to minutes because we were given 10 minutes. So when t equals 10, the temperature is now 65 degrees. So let's put that in. So 65 equals 23 plus 77e. The t is 10, so I'm going to write that straight away as 10k, because we know this process now. We've done that a few times. So let's minus the 23. So therefore 42 equals 77e to the 10k. Let's divide by the 77. So I'm going to write the e to the 10k first. Now I'm just going to leave that as 42 on 77. You know how much of a fan I am of exact values. Let's just take the log of each side. It also saves picking up a calculator, which makes it easier too. Log and e undo each other. 10k equals the log of 42 on 77. Let's divide by the 10. So k is equal to 1/10 log 42 on 77. If you do want it as a decimal, I got negative 0.0606 to 3 significant figures. Now, again, I've stored that in my calculator as my A value in my calculator. Now, I am going to write out what my final equation is at this point. It's always a good idea to do that, and sometimes the question will specifically ask you to do that. And it's a common thing that people forget to do, is to actually write this step. They often stop there and forget to write that line, which is really important. Again, I've written a decimal here, but the exact value is stored in my calculator, so I don't mess it up. Also think about, why is k a negative? It's a negative because it is a decay situation. So decay is when k is negative. The question asked us, when does the temperature hit 25 degrees? So 25 equals 23 plus 77e to the negative 0.606t. We're solving for t time when the capital T temperature is 25 degrees. So as before, I'm going to minus the 23 off each side. So this is just now 2, 77e to the negative kt. I'm being a bit lazy there. In an exam, do write the number or write something there, whether it be the exact value or just even just 0.06 is fine. So again, I'm going to turn it around. So e to the negative kt. Actually, sorry, I shouldn't really write negative there. K is negative already. Put the negative if you're going to put the actual number, but I'm just going to leave it as k, which is a negative number stored into my calculator. So that's 2 on 77. Let's take the log of each side. So log and e undo each other. We've got kt equals log of 2 on 77. So let's divide by the k. So t equals log 2 on 77 divided by our k value. And when I put that in my calculator, I got 60.228. Now remember, that was in minutes. I am going to press the little call button again to turn it into, now normally that's hours, minutes, seconds, but you can actually think of it as minutes, seconds. You just got to be careful here because that's now 60ths of a second. So just be a little bit careful there. But that was 60 minutes and 13 seconds. Oops. Now, I did also want to just mention about limiting values of this equation. So what we might be asked is what happens as t goes to infinity, as t gets bigger and bigger and bigger. And you can put in some really big numbers for t here to actually see what that happens. But also you can think about it graphically. So this is a negative number, and e to a negative number. So if you just have e to the x, that looks like that. But e to a negative number are these numbers down here, and as you go more to negative infinity, you can see you're getting closer and closer and closer to 0. So e to a negative number, a negative number near infinity, is going to be 0. So this is like 77 times 0. So t, as little t goes to infinity, capital T goes towards 23 plus 77 times 0. And that, of course, just equals 23. So we called that 23, that's the limiting value for that equation.